Hello, everyone. My name is Suzie Imber. I'm an associate professor of space physics, and I'm delighted to be the recipient of the Rosalind Franklin Award this year. I'm going to give a lecture today on space weather, implications for life on other worlds, where we're going to talk a bit about space weather at the Earth and in our solar system, and then think about extrasolar planets and the implications for whether they could one day be habitable. So thank you again to the Royal Society for hosting this lecture and giving me this wonderful award. And let's begin. In this picture here, we have the sun on the left and the Earth on the right, and the sun is emitting a hot gas or plasma all the time called the solar wind, which is coming off the surface in all directions. It's also dragging the sun's magnetic field out with it into the solar system, and that forms the solar wind. On the right is the Earth, and around it in this blue region is something called the Earth's magnetosphere, which is the region of space dominated by the Earth's magnetic field. The study of space weather is studying how the sun and the solar wind impact the Earth and the Earth's magnetosphere, and of course can be extended to other bodies too. Space weather has a huge impact on us here on the Earth's surface, although it might not be immediately apparent to all of us every day. There are a number of ways in which the sun can impact the Earth, and they're listed on the left. So Xrays, energetic particles, coronal mass ejections, which are explosions of magnetic field and plasma from the solar surface out into the solar wind, which eventually hits whatever's in their path, which could be the Earth. And the way in which it can affect us, well, it can cause disturbances to the ionosphere. That's the region above the atmosphere. And that makes communication difficult. So it disrupts our communication and it disrupts our GPS systems. It can cause airline flights to be rerouted because of these communication issues. It can directly damage satellites, both instrumentation and the stability of the satellite's orbit. It can cause issues with our power grids. So in the ionosphere, massive currents flow driven by space weather, driven by the sun in essence. And those mirror currents in anything on the Earth's surface that's long and metallic. So for example, the electrical power grid system or pipelines. And of course, if we have currents, extra currents flowing through the electrical power grids, then that can cause damage. And also, of course, damage to astronauts. They get a high dose of radiation. The nice thing is that space weather causes beautiful aurora. So you might see northern lights and southern lights being very bright, expanding to lower latitudes, maybe even over the UK. But you can see there's massive disruption here. And this doesn't happen every single day. These big events are very rare. But you can imagine if one did happen tomorrow, it would have a huge impact on our society because we're so dependent upon our technology, whether that's using our satellite systems, or GPS systems, or our power grids. The biggest event that we know of happened in the 1850s. It was called the Carrington event. And it didn't have a huge impact back then, again, because they weren't so dependent upon technology. But that's the biggest event we know of. Smaller events have happened periodically since then. These are representative images of the sun, one taken per year over an 11-year period. And you can see the sun was quiet in 1996. Solar activity dramatically increased towards 2001 and then decreased again as we headed back towards 2006, the end of that solar cycle. So the sun has this 11-year activity cycle. It's not exactly 11 years, and the intensity changes from cycle to cycle. It's very difficult to predict. And indeed, the sun more recently has become more unpredictable. But you can see that we would expect to see an increase in solar activity about once every 11 years and then a decrease again. Interestingly, once every 11 years, the sun's magnetic field flips over, the poles flip, similarly to the way the Earth's field flips over much longer timescales. So we can look at the sun and try to understand how that dynamo flips and then apply that knowledge to understanding how the Earth's dynamo flips on timescales of many millions of years. So solar activity is variable. What can we do? Well, we can launch spacecraft to go and get close to the sun and try to understand the physics behind this space weather and these events that erupt from the solar surface. This is an artist's impression of the Parker Solar Probe, launched recently, which is heading extremely close to the sun to do exactly this. But we've only recently developed the technology to enable our satellites to get that close to the sun. For many decades, we've been looking at the sun from the Earth and from the near-Earth environment. And so in this image, you can see several points in the Sun-Earth system that are marked L2. These are the Lagrange points. L2 is where James Webb actually just went to, so that might be familiar to you. L4 and L5 are ahead of and behind the Earth in its orbit. L3 is the exact opposite side of the sun to the Earth. And L1 sits just upstream of the Earth, about 1 million miles away. And it's a really useful point that we've had a spacecraft sitting there for many decades now. These points are points of relative stability where we can have a spacecraft in that environment for an extended period. We've had spacecraft at L1 because we want to know what's coming from the sun and what impact it will have on the Earth. This is a point where we can keep a spacecraft, like I said, for an extended period. And we're looking at things like the solar wind velocity, the solar wind density. We can measure those remotely to some extent, but we also need to know the magnetic field of the solar wind. And that's very difficult to monitor remotely. So by having a spacecraft at L1, we can measure this about an hour before this event will hit the Earth. It's not much warning, but it's the best that we can do at the moment. And the satellites then that are looking at the sun, trying to look at these events, do so over a variety of wavelengths, which you can see on the left-hand side. Different features will appear in different wavelengths because they're looking at different altitudes as we look down at the solar surface. And so you can see different features popping out in some of these different wavelengths. On the right, you can see an image from SOHO, one of our satellites that has been a workhorse for many years looking at the sun. It's a composite image, so we're looking at the sun in a particular wavelength, and behind it you can see this bright white explosion. These are the kind of events that we're looking for, because if we can identify these and try to understand their characteristics close to the sun, we can expand them outwards using computer models. This again is an array of wavelengths. We're looking at a solar flare here just to give you, again, some idea of how different wavelengths pick out different aspects of a particular feature. This is some model runs actually run by the Space Weather Prediction Center. And what they can do is if you give them good initial conditions near the sun, they can input these into their model and then propagate the solar wind outwards. So propagate this particular event through the solar system. What you can see at the top is you're looking down on the sun. The green dot is the Earth. And blue and red are ahead and behind the Earth in the Earth's orbit. We have some spacecraft there, stereo A and stereo B. The color in the top section is plasma density, and the bottom section is radial velocity. So two parameters that we're really interested in to try to understand how significant the space weather event might be. So if I press play, you can see that they're able to propagate the event throughout the solar system. They're able to predict what we'll see at the Earth and at stereo A and B. And these models are incredibly useful to us when we're trying to understand whether we should be worried about a space weather event, which way it might go and what it might hit. Now, I just have the Earth here, but they're able to extend these models further. So we could see if this event would hit Mars, for example, or inwards, we could see if this would have hit Venus or Mercury. This is going to show us exactly in more detail how the sun interacts with the Earth. So here we have the solar wind coming from the sun. It's traveling at about 400 kilometers per second. On average, it takes about a few days to reach the Earth. And the Earth here, you can see, has blue field lines around it. And these magnetic field lines interact with the solar wind. You can see that's magnetic reconnection, a reconfiguration of the magnetic field there on the sunlit side, the day side. And energy and momentum are transferred into the Earth system and build up and up and up in the system until they cannot be sustained. Energy is released explosively, again through magnetic reconnection. Particles are tied to field lines and travel down them at speed, get accelerated down them until they hit the Earth's atmosphere and make it glow, causing the Aurora borealis, northern hemisphere, and australis, southern hemisphere. This is particles making the atmosphere glow. Here we're looking at the Earth from the side, and I want to show you how we measure space weather using a variety of different techniques on the Earth. What I should say about this actually is that we can remote sense large areas of the magnetosphere by making specific measurements. So here you can see the lines there are the Earth's magnetic field lines. If I tug on one of these field lines somewhere, then I will feel it further along the field line. So if I move a field line on the far top right-hand side of your screen, then the motion associated with me tugging that field line will be observed at the Earth's, above the Earth's surface, in that the footprint of that magnetic field line, where that magnetic field line comes to the Earth. And so if I can look and understand how all the magnetic field lines are moving close to the Earth in the northern hemisphere and the southern hemisphere, then I can use that as a proxy for understanding the dynamics of the entire magnetosphere, because all of these field lines come down and funnel down into these two regions. So here I've put on top of the Earth, I've put this constellation of satellites. This is the Iridium constellation. They are a communications network, and they have a magnetic field instrument, a magnetometer on board. And so they are measuring magnetic field all the time. We can get that data, and that tells us about the currents that are flowing in the ionosphere, the region above the atmosphere. So we can gain some understanding of these giant currents, and these currents often cause disruption on the Earth's surface. Another thing we can do is we can use radars. This is one of a network of radars called SuperDARN, the Super Dual Auroral Radar Network. And they sit near the poles, this huge network of radars pointing up, and they work a bit like the Doppler effect. So if I fire a radio wave at a moving object, it will bounce off that object and come back to me. And in doing so, its frequency will have changed. And the frequency will have changed depending on the velocity of the object it hit. So if it's moving away from me or moving towards me, the frequency will shift one way or the other. The radars use exactly the same concept. So we fire our radio waves up, they bounce back off of particles in the ionosphere, so high up above the atmosphere, and they come back to us. The change in frequency tells us the motion of the plasma up in the ionosphere, and we build up a picture using lots and lots of radars till we understand the global dynamics of the plasma up in the ionosphere. Now, I mentioned briefly earlier that magnetic field lines and particles are tied together. So if I understand the motion of the particles, then that is also the motion of the magnetic field in that region. And again, if I understand the motion of the magnetic field close to the Earth, then I can also interpret that to understand the global dynamics of the system. So the radar is a really powerful tool. I can also look down on the Earth with a spacecraft and look at the entire aurora, the southern auroral oval. And you can see during this image, during this video, the image is changing. The aurora is dynamic. It's getting brighter and dimmer. Features are appearing. It's expanding and contracting. The details of these images, again, tell us a lot about the dynamics of the system. They're measuring the particles that have reached the bottom of the field lines and hit the atmosphere. That's what we see as the aurora here in ultraviolet. And so that obviously tells us a lot about where these particles are hitting the Earth. That tells us about the magnetic topography. And so we can learn a lot from these global auroral images. So these are all ways in which we can remote sense the broader magnetospheric activity. But the other thing we can do is launch satellites themselves, and they can take incredibly detailed measurements of their environment. We've recently launched some spacecraft that you can see in this picture here, a constellation of 4 spacecraft. But for a few years, we've had constellations of spacecraft orbiting the Earth. And that's really, really valuable because these 4 spacecraft can give you amazing information. If you put them in the right place, so in an orbit that is in a good location to see a feature that you're interested in, then they often are in the right place to measure with incredible detail this feature, this phenomenon, this whatever you're looking at. And so spacecraft are great, but space is massive. And so we run into difficulties because we can't populate the entirety of the near-Earth environment with spacecraft. So they're brilliant for looking at features in detail and really working out fundamental physics, but we don't have enough of them. So these remote sensing techniques complement our satellite measurements. We also have models, and models, again, have become incredibly powerful over the last decade or so. Here's an example of a model. The lines are the magnetic field of the Earth. The color is density, plasma density. And so you can see that our model is changing and shifting. We're going to have an event in a moment that hits the Earth, and you can see that we're able to model the response. That's really helpful. I can compare that with data, see how accurate that model is, and then I can use it to interpret other features that perhaps I wasn't able to directly measure because I didn't have instrumentation in the right place. So I can verify my model is correct and then look a bit more at the different features inside of it. This next one is actually a model of the Carrington event. So here's that massive space weather event that hit the Earth in the 1850s, and this is what it would have done to the Earth. And this is useful because, as I mentioned, these big events don't happen very often. So if I really want to understand them, then the extreme end of the events, I have to model them because I can't see them. Now, moving past the Earth, one question that's always been fascinating for us is to understand Mars and its environment. And so the left-hand side shows kind of Mars as it is today. And the right is showing you Mars as it might have been about 4 billion years ago. And you can see it had an atmosphere, it had liquid oceans. It actually also had a magnetic field, although you can't see it there. And somehow it went from the right to the left. And the question is how and why? Well, we know that Mars's magnetic field switched off, we suspect about 4 billion years ago. And we think that that precipitated loss of the atmosphere, loss of the oceans, and Mars turning into the world as we see it today. If Mars doesn't have a magnetic field to protect its atmosphere, the solar wind can strip it away. And this is a picture, an artist's impression based on data taken by a spacecraft at Mars called MAVEN. And here you can see the sun, and you're looking at particles being stripped off of the planet by the solar wind. And we thought that this really was the primary mechanism by which the atmosphere was lost at Mars and the oceans were lost at Mars when the magnetic field switched off. But now we think there may be something else to this, because we have some data taken by the Curiosity rover at Gale Crater showing that the surface is hydrated. So we have hydrated minerals. And that means that it could be that some of the surface water actually is still found in the crust and the surface layers of Mars. It's not sitting above the surface, but it could be in the surface itself. We also found evidence of subsurface oceans and lakes on Mars. And so we think that there could be quite a lot of water left on Mars, actually, just not sitting on the surface. I want to show you this because I want just to describe Venus briefly. Now, Venus doesn't have a magnetic field of its own. So you might expect its atmosphere to have disappeared in a similar way to Mars's, but it hasn't. It has a very, very thick atmosphere, and that is the key. So its very, very dense atmosphere is able to hold off the solar wind. And although there is a lot of atmospheric loss, and you can see it disappearing down the Magneto tail there, there's also atmospheric replenishment. And so Venus is able to hold on to its atmosphere, even though it doesn't have a dynamo magnetic field of its own. So just to bear in mind, there are some circumstances in which induced magnetospheres can be generated with very, very thick atmospheres. What I want to talk about now actually is Mercury, because Mercury's been a huge focus of my research over the years. Here you can see a transit of Mercury. It's going across the surface of the sun. This is an image taken from Earth's orbit, just to show you the closeness of Mercury to the solar surface. Now, it's interesting to me, again, you're looking at different wavelengths here, by the way, in the background. It's interesting to me because Mercury has a very weak magnetic field, and it's very close to the sun. So it experiences extreme space weather. It experiences one of those Carrington events every day. And so my work tries to understand Mercury and these extreme space weather events and understand the physics behind them, so I can apply that knowledge to understanding the Earth and its environment if a big space weather event came along. We have a spacecraft that has orbited Mercury, just the one. Its name was Messenger. It was a NASA mission. And it made some amazing discoveries about Mercury and its environment, just being the first spacecraft to orbit the planet. It looked in detail at the surface, mapping the volcanic plains, looking at scarps and ridges, features that formed as Mercury cooled and shrank that we don't see elsewhere in the solar system, and indeed impact craters that we think formed just under 4 billion years ago. In fact, they formed on all of the terrestrial or rocky planets. But at many planets, so for example, the Earth, many of them are filled with water. We have weathering, vegetation. We can't see them very clearly anymore, as well as resurfacing of the Earth's surface. So Mercury's surface has remained pristine, except for when volcanoes have gone off and filled them in. That's why the plains look so smooth. There are regions where there hasn't been volcanism, and we're able to really look at the impact craters, which tell us something about the late heavy bombardment itself. Messenger also looked and solved actually a very interesting puzzle around deposits on its surface. So the idea around the image I'm showing you here on the right-hand side, the yellow is taken from the Arecibo radio telescope in the 1990s. They looked at Mercury and they found these really bright regions on the surface, and they didn't know what they were. And this was a mystery for a really long time. Then Messenger arrived and it took data and it made photographs of the surface. And if you superimpose those in gray here with the radar bright regions over the top, you can see that the radar bright regions match up with these very deep craters called permanently shadowed craters. They're impact craters that are very deep, so deep that the sun cannot hit the bottom of the crater. And so as a result, that crater, the bottom of the crater, is able to stay so cold that we can have solid ice. Now, this is a pretty bold statement because the day side of Mercury is at 450 degrees. And so you might think that actually the temperatures are so severe on Mercury that they should have melted all of this ice. But there are pockets where the temperature is so low, the ice remains. And this solves a mystery when we realize that these two features lined up. Messenger also looked in more detail at the crust of Mercury and made some really interesting measurements that allowed us to determine that the core of Mercury, the metal bit in the middle, is massive. So at the Earth, that core extends to about half of the Earth's radius. At Mercury, that's about 85% of the radius of the planet. So it's nearly all core. Around the core at the rocky planets, we find the mantle, this rocky area around the edge of the core. At the Earth, that's a huge, deep mantle. 50% of the Earth's radius is mantle. But at Mercury, we find hardly any mantle. And the question is why? What happened? Was the outer layers, did they somehow get blasted off and disappear? Did it form the way we see it today? We don't know the answer at the moment. I'm really interested in X-rays at Mercury. And the X-ray instrument was predominantly designed to measure the composition of the surface. So X-rays are given off from the sun. They hit the sunlit side of the planet, are absorbed by the particles there, and an X-ray is emitted, called a fluorescent X-ray. And we measure those X-rays. We can add up all of these X-rays together, and the energy of each X-ray tells us the composition, tells us the atom that gave off that X-ray. So if we add all of these up, we build up a big picture of what the surface of Mercury is made of. And that's what X-ray instruments like the one on Messenger are designed to do predominantly. So I was interested in these, and some colleagues at Leicester were interested in understanding how we see these and where we see these, looking towards a future mission. But we also plotted the X-rays on the night side of the planet, the dark side of the planet. These cannot have been generated by the sun because they're on the dark side. And we found X-rays coming off of the dark side. And this was a really interesting puzzle for us. On the left of the screen here, you can see Mercury side on. We're looking at its magnetosphere, and it looks similar to the Earth. It's very small, it's compressed, it's because it's close to the sun and the field is weak, but it has all the same features that you would see at the Earth's magnetosphere. If I press play now, you can see this is looking at the Earth. The slightly grainy image I've selected because you're looking from the side at the Earth, so you can see the aurora in the northern and southern hemispheres. Now, if I plot the X-ray data on the left from Mercury, so the right is the Earth in the UV, the left is Mercury, what you can see is two bands of X-ray emission. They're actually symmetric around the magnetic equator of Mercury. Now, Mercury's magnetic equator is offset from the center of the planet to the north by a fifth of Mercury's radius. A really interesting feature of Mercury is this offset magnetic field. But the emission is symmetric about that magnetic equator. It looks kind of similar to the one that you see at the Earth on the right-hand side. And indeed, we determined that it had been formed by a very similar process. So acceleration of particles down magnetic field lines caused ultimately by the interaction of the magnetic field of the sun with the planet. These particles fly down field lines. At the case of Mercury, there is no atmosphere for them to hit. And so they directly impact the surface and cause the surface to give off X-rays, which we are then able to detect. So the instrument wasn't designed to measure these night side X-rays, but having observed them, now we're able to use these to our advantage and indeed to probe a whole new area of physics at Mercury in some senses, because we can now globally image the X-rays if we build up this picture over time at Mercury and really gain an understanding of the aurora. And as I said, the aurora gives us a global view of the environment. So these are really useful. The reason I'm really excited actually about this X-ray aurora is not just the discovery, but also the fact that we're working on a mission to Mercury at the moment. It launched in 2018. It will get there in 2025. So it's about halfway there. And it's called Bepi Colombo. It's a joint European-Japanese space mission. And on board is the instrument you see on the bottom left of the screen there. That is an instrument that we built at the University of Leicester. It's an X-ray instrument, and its function was to look at the composition of the surface. So looking at the sunlit side and understanding in incredible resolution, much better than previous instrumentation, the composition of the surface. This instrument was designed 20 years ago to do that function. And since then, we discovered the Aurora, the night side X-ray Aurora. And so now we're working on also being able to use our instrument to look at the night side Aurora, as well as its primary function, which was to look at the composition. So can we tweak the way that we use our instrument to also detect this night side emission and use that to understand Mercury's Aurora? So that's what I'm working on at the moment. Of course, it's not just Mercury and the Earth that have magnetic fields. The other planets do, Saturn does, Jupiter does, and you can see the scale size increasing here. Jupiter has a vast magnetic field. Indeed, the Earth's, the sun's magnetic field also, if you look at the heliosphere on the bottom left, extends out and defines the extent of the solar system. And so we understand that planets have magnetic fields. Many have magnetic fields that they're useful for holding on to your atmosphere and enabling life, perhaps, or enabling good conditions for life by having liquid water and an atmosphere. And that's, in fact, the interaction of the magnetic fields with things like the sun's magnetic field generate aurora. And so let's think about what we can do looking at other planets. So quickly, here's the aurora, Earth, Saturn, and Jupiter. Earth, that's actually taken from the International Space Station, that image. Saturn and Jupiter, you can see, have aurora as well. This is taken by the Hubble Space Telescope. It's ultraviolet. It looks similar to the Earth's aurora. It's slightly different. It's generated in a slightly different manner, but still aurora is indicative of a magnetic field on those planets. I should add Mercury's aurora in there too, actually, to this picture. We want to look now at other planets, extrasolar planets. Could they have a magnetic field? We've discovered thousands of these over the last few years, and indeed we believe there are billions of these planets orbiting other stars, and we detect them primarily at the moment using the transit method, where the planet goes in front of the star and the light of the star dips as a result. The depth of the dip is proportional to the size of the planet and how close it is to the star. So it's easy to pick up large planets orbiting really close to their star. Here's a small planet. You can see the dip is much, much smaller. So they're harder to detect using this method, but we're finding more and more of these. And indeed, NASA and ESA are launching just a huge number of spacecraft and missions, as well as using ground-based instrumentation to find these exoplanets. Of course, I've put James Webb front and center there. It launched on Christmas Day last year. But there are many other satellites as well that are looking and actually using different techniques to try to find these exoplanets. One of the most famous exoplanetary systems that has been found is called Trappist-1, found by Spitzer. 7 terrestrial planets, so 7 rocky planets, 3 of which are believed to be in the habitable zone of the parent star. So that means the zone in which there could be liquid water. This is fascinating to us that we're able to find these kind of planets. It might be the right distance for liquid water, but does it have liquid water? Well, now we have to start thinking about the rest of the environment. So could it have a magnetic field to protect an atmosphere, to protect liquid water from being stripped away by the solar wind of that star? This is another really fascinating one. This is a planet called GJ367b. It's a typical astronomy name. It has a mass about the same mass as Venus. It takes about 8 hours to go around its parent body, which is a red dwarf. So it's very close to its parent body, only has an 8-hour orbit. But its parent body is a red dwarf, which is very different characteristically from our sun. And so the habitable zone is much, much closer in. And that means that this Venus-sized planet is in the habitable zone of this red dwarf star. What I'm showing you here actually is Jupiter and one of its moons, Io, which is producing a lot of gas all the time that gets ionized to form this sort of cloud of ionized particles. And those interact with Jupiter's vast and powerful magnetic field. Particles get accelerated down magnetic field lines and they towards Jupiter's poles. You can actually see this in the aurora of Jupiter. You can see a spot corresponding to the foot points of this moon, where the magnetic field lines that go from this moon actually encounter Jupiter. You can see that a spot there. You can also see as particles get accelerated, they give off radio waves. And the idea that we're thinking about here is that we won't be able to see the auroral spot, but could we detect the radio waves that are generated as a result of the interaction between a planet and its moon, or indeed a star and a planet? Is it possible for us to detect those and know that there are magnetic fields at work here? The answer is maybe. And that's one of the things we'll be working on looking forwards. We have actually detected low frequency radio waves. I say we, but actually this isn't my research, coming from a brown dwarf. This is a failed star, but we've been able to detect low frequency radio waves indicative of maybe some kind of aurora. I want to emphasize this as an artist concept here, some kind of aurora or some kind of auroral processes. Maybe it has a body orbiting it. And so we're seeing this interaction of these two bodies generating aurora somehow on this body. This brown dwarf is just wandering through space. But just being able to detect these, and with new detectors coming online over the next few decades, this might be a really promising avenue of research and trying to understand better how these exoplanetary systems have evolved and the way that they look, and maybe whether they could be habitable. Okay, I'm going to wrap up my lecture there. I want to thank you again for coming along to listen to it. Again, huge thanks to the Royal Society, both for the honour of this award and also for hosting this lecture. And I'd love to take any questions that you may have. Thank you.
Well, thank you, Suzie, for a brilliant talk. We've had a fascinating trip through the solar system, and you've described the phenomenon of space weather and stressed the importance for the development of life on other planets of both liquid water and magnetic fields. If you'd like to ask a question, please type it into Slido. Maybe I can just start off with one to begin with. Could you tell us just a small amount about the project that you're planning to do with this award?
Yeah, great. Okay, so the very generous award is going to fund a series of weekends at the university. So the idea is that I'm going to sort of look across the country, invite students, particularly students that maybe haven't had opportunities to being located near science centres or being involved in science projects before. I'm going to sort of target specific areas and invite students to come to the university for weekends, focus on physics. There'll be some GCSE students and some A-level students. And it's going to be kind of all about improving their confidence. It's going to be about the fact that they're physically visiting a university. Some of these students may not necessarily have friends and family that have been to university before. So I also just kind of want to show them that the university environment is welcoming and friendly, and it's not an intimidating place. Kind of grow their interest in physics and sort of support them as well from then on with their studies and applications, and hopefully try and kind of get a group of students really sort of to follow the path of physics. That's the idea.
That's great. Well, Leicester is a great place to go. You have a wonderful space centre there. Yeah. So we have a question from Cassie Spence here. Said, Suzanne, I'm considering doing physics at university. How did you first become interested in this field?
That's a really good question. I was kind of interested in physics and maths for a while, sort of GCSEs and A-levels. I focused on maths, physics, chemistry, and further maths A-levels. But certainly I wasn't sort of targeting space science or anything. That I just kind of tumbled in that direction. So sort of a series of interactions and good luck and being in the right place at the right time and sort of having a conversation with various people kind of got me involved in space science. But physics I've been interested in, maths I've been interested in for a really long time. It's kind of something that sparked my interest at school, actually.
Mm-hmm. Okay. Charles Draper asked, why doesn't Venus have a magnetic field?
That's a really good question. So Venus, what you need to generate a magnetic field is you need a metallic core, you need sort of a liquid metallic core actually, and you need some convection in that core, and you need the whole thing to be rotating, and that gives you currents that drive the magnetic field. Venus has almost all of those things. So it has a liquid metal core. And the issue with Venus, actually, is a couple of issues. One is that it's rotating really slowly. And so that's a big barrier. And the other is that it finds it quite difficult to lose heat. So it's difficult to get the convection that you get in the core through sort of heat loss from the planetary system. So there are a couple of reasons why Venus doesn't have one. The question about Mars actually is another really interesting one that actually we're still trying to find out the answer to. Why does Mars not have a magnetic field? It's not the obvious, it's just cold and dead out there answer that you might expect. It's much more complex than that. So there's ongoing studies to try and figure the answer to that one.
Harry Greetorex asks, what are your thoughts on or hopes for the future of space weather research during solar cycle 25?
Yeah, so the nice thing is that, and this is not by chance, is that our mission to Mercury is going to arrive during high solar activity. We actually need that. If we don't get any X-rays coming from the sun, then we don't get any measurements of the surface of the planet. So that wasn't just chance. But we've got a series of missions that are designed to take advantage of the solar maximums, tell us more about the system. And these include other places in the solar system, not just Mercury, though I'm obviously excited about Mercury. Lots more Earth missions going on as well over the next few years, launching. We have to be slightly careful because the last solar minimum, we launched some really interesting spacecraft expecting the solar cycle to go up. And it didn't. We had this extended solar minimum and our satellites didn't really see, certainly in their prime mission, what we were hoping they would find. So the solar cycle doesn't always play ball, and we have to be aware of that when we start designing really expensive missions to look for really specific things.
And Nick says, do we know of any stars that with a magnetic field that doesn't fluctuate as much as the sun's, and would that make a difference to the likelihood of life in that?
Oh, that's a really good question. It's actually a really broad question that I don't know the answer to. There are lots of people studying stellar magnetic fields, and I know they exhibit just a broad range of activity levels. I don't know if we know enough to be sure that there are any that are super stable, that don't have, you know, huge fluctuations in activity. If you think about the Earth, though, despite these fluctuations in activity that I mentioned, life is still habitable at solar minimum and solar maximum. So it's not really a case in our system of it causing, you know, mass extinction.
And then someone else says, should Ewan Haggerty, should the probability of the presence of a planetary magnetic field be included in the Drake equation? Maybe you can say what the Drake equation is.
Sure, yeah. So the Drake equation is an equation with lots of different variables, trying to discover kind of the probability of life existing somewhere else. And so it includes lots of different variables that sort of factor in, and there's lots of bits of it that we don't quite know yet, so we can't quite narrow down. Although discovering worlds with the potential for liquid water in the right distance from their star is obviously a big step forward. There are some big leaps, though, in the evolution of life. For example, we think that life formed quite quickly on the Earth, but complex life certainly didn't form quickly. So there are some interesting things that we don't quite know about. So the Drake equation is basically describing the probability of life elsewhere. Yeah, it could be that actually magnetic fields are so important that they should be included. I don't think we really understand yet how many of the terrestrial planets have their own magnetic fields, because we only know for sure the ones that we can sort of observe in our own solar system, and that has, you know, there aren't very many. So we need to find out more. But yeah, certainly it's an important factor, I think.
Adam Beyer says, I saw on BBC some time ago that the Earth's magnetic poles are moving. Does that have any effect on our magnetosphere and change the risks of adverse space weather?
So yeah, the poles are moving. One is moving faster than the other. And that's quite interesting to think about sort of the physics behind why one pole is moving faster and the other pole is moving less fast. So the North Pole is moving really quickly, the South Pole not moving that much at all at the moment. Yeah, it is going to affect the region where you might expect severe space weather to happen, because that's relative to the magnetic poles, and the poles are moving. So yes, although then over sort of long time scales, they're moving significant distances. Sort of year upon year, they're not moving that far. So you wouldn't expect to see the effect over short time scales.
Yeah. Oliver Williamson is 10 years old and says, would it be possible for you to restart a magnetic field on Mars, even though its magnetic field has already been lost?
Oh, that's such a good question. And actually loads of people have asked that question. So for a 10-year-old, that's a brilliant question to be asking. There have been various flippant comments about, oh, let's just nuke the interior of Mars and we'll make the magnetic field work again. That's definitely not the answer. Until we know why it switched off, which we still don't understand, it's going to be difficult for us to even begin to think about what we could do. However, here's an alternative. A magnetic field is protecting the planetary environment. So what if, and this is still in the realms of sort of science fiction at the moment, but what if upstream of the planet, you could put something that had a massive magnetic field that could deflect the solar wind around the planetary body? You know, people are thinking about things like that to possibly do a similar thing. If you can't restart the planet's magnetic field, which you probably can't, can you do anything? The other thing to note is that Mars's global field has gone, but there are still kind of pockets of magnetic field, remnants of that field that are stored in the rocks. So there is quite an interesting magnetic structure there on the Martian, in the Martian rocks, to think about as well.
And Amelie says, I'm 4 years old. And I love space. Suzie, why does the Earth have a magnetic field?
Wow, you're 4. That is an amazing question. That is, yeah, okay. So we'll go with it because it's a great question, and we'll see what we can do. So the Earth has a magnetic field because the inside is made of metal, because the Earth is able to cool down, and because the Earth is spinning. And those things together give you your magnetic field.
Well, I think time is actually getting on. We'd scheduled 15 minutes for questions. So I'd like to thank you, Suzie, for a brilliant talk and very good answers to the questions. We wish you luck with the new space mission to Mercury.
Thank you.
Hearing about your discoveries there. I'd like to remind the audience that the next Royal Society lecture is the Bakerian Prize Lecture. It'll be given by Professor Michelle Simmons on quantum electronic devices on the 1st of March. And hopefully that will be in person at the Royal Society in London. But if you're not able to come, you will still be able to watch it online. Thank you.